Okay, for the first talk this morning, we are very pleased to have Herwig Hauser, who will tell us about phylogenetic trees and moduli of endpoints.
Thank you very much. Welcome, everybody. Good morning. I'm very happy to talk here, not only because it's a stimulating atmosphere, but also because I very much like the topic which I'm talking about. Of course, you always like your own topics, but in this case, it's a new topic for me. I learned it through Josef Schicho, and at the beginning, I protested. I didn't want to know about it, but then he convinced me. So now I try to convince you that it has some charm. This is Josef Schicho from the University of Linz in Austria. So the topic will be endpoints in PD. It will be very gentle and elementary talk, and I finish in time so that Sergey can continue more advanced stuff. But D is here an integer, and the main cases I will discuss are D equals 1. Then I will talk a little bit about D equals 2. And I'm not going to talk about D equals 3, except a very little bit. Okay. And as you all know, these are the Korean first numbers 1, 2, 3. And I'm only familiar with them not because Jun Hu is here, but my 3 boys learned Taekwondo when they were kids. And they were always counting at home, Hana Dul Set, Hana Dul Set. So let us do Hana first. So what we will need is a little bit of terminology. An n-gon in PD is just n tuple of points in PD. And I will select inside this n-gon a d plus 2 gon, d plus 2 gon of x is generic if no d plus 1 of the point of this n-gon of d plus 2 gon lie on a hyperplane. No d plus 1 points lie on a hyperplane. For d equals 1, we just have 3 pairwise distinct points. Xi, xj, xk appearing in this n-gon. For d equals 2, it will be a non-degenerate quadrangle. For the quadrilateral, so something like this. And then goes on. And we are looking at these n-gons with respect to the action of PGL d plus 1, PGL d plus 1, x of PD, PD to the power n. And we want to study the orbits of this action on n-gons. The orbits and the orbit space. So that's the outset. And I guess you're all familiar with this situation. PGL d plus 1 acts d plus 2 strictly transitive. So whenever you have a d plus 1 gone, which is generic, then you can send it by the action of PGL d plus 1 to any other such d plus 2 gone. Typically, 3 points can go to any 3 points if they are pairwise distinct. And the non-degenerate quadrilateral goes to any non-degenerate quadrilateral. And the element of PGL d plus 1 which does this is unique. This is the meaning of strictly transitive. Okay? This has to do with stability, appearing in the work of Deligne-Mumford and so on. So the goal will be, and that's a very classical goal, describe P d to the n, and now I take out those which are non-generic in a certain sense. Let's not specify this. So you take the nice n-gons, then you take them out. Okay. So this is the first instance, that's relatively easy, and then you want to find the natural compactification. And natural is a little bit a matter of taste, but there are various proposals and many of them coincide. Okay.
Sorry, what is S?
S are those n-gons which I don't want to consider. Those are special ones. For instance, if all entries x1 up to xn coincide, I want to keep them out. I will specify this in a moment.
Oh, okay.
It's just the general outset, the philosophical part. Okay. So for d equals 1, we will take S delta and the big diagonal. So we take n-gons x1, xn, all xi pairwise distinct. And then we have PGL2 acting in these n-gons. And we get the quotient P1 to the n minus delta n mod PGL2. It usually is denoted M0n in the terminology of classical terminology. For today, I want to call this just UN, not to mix up with the classical situation, but it's the same object. Okay. So that's the orbit space.
Just to clarify, the points are labeled, right?
The points have their indices, yes.
Right. So when we permute them, it's a different.
Yeah, I'm not doing this today. Yeah, that's why. Okay. How does this? I have to get used to. Maybe it's better to talk in the middle now, so we don't need it. I was joking this morning, but I did not know that I would have to work here. So here you may add, this would be M0n, and then you get M0n bar, and you could also consider this curves of any genus, but I stick to genus 0 here. Compactification. Now, this compactification is defined by the concept of n-pointed stable rational curves. But I'm not going to use this today, except at the very end of my talk. Okay. I want to propose a different approach to this space using phylogenetic trees. Okay. So Let us do an example. What does it mean to compactify? It means to add limits. But it's up to you how you want to define limits, how many different limits you want to consider. So if you write P1 equals K union an element at infinity, and you take X in P1n, then by the action of PGL2, X will be equivalent. You can organize your life. So again, I take it outside. The diagonal, you can make the first 2 and 3 entries equal to 0, 1, infinity, and then you continue in some sense as you want. Here you have x4 up to xn. And this is just a shorthand for 1, 0, 0, 1, and 1, 1. These 3 points. Okay, but of course I could put these special values at any coordinates I want. It's not necessarily the first 3. So here I have a selection because it's easy to write it like this. Okay. So now let's take n equals 4. And let's see what we could understand by limit of such an n-gon. So we have, let's say, t in k minus 0, 1. I exclude these, and we take x equal 0, 1, infinity, and t. So t is distinct from these others. And we want t go to infinity. So we end up with 0, 1, infinity, infinity. This is certainly a decent limit, but we are looking at x up to the action of PGL2. So this one is equivalent to y. If we write it like this, I have to take care. If we bring the 3 special points to the last 3 coordinates, we get a 1 over t here. Okay. And now if we take the limit, we get something different. We get 0, 0, 1, infinity. And these are now no longer equivalent at PGL2. So you see that if you have a family of orbits here, and you want to define something like a limit, it depends where on the orbit you are, and accordingly you get different n-gots. Okay, and this has to be taken into account when you want to define the compactification. Okay.
You can, of course, decide to identify these two, so just declare these 2 points the same.
Yes, but if I want to end up here, I better don't.
Okay.
I said it's a matter of taste. You could just take a 1-point compactification, but that's not interesting. Okay. So I want to do everything in the most natural way without thinking, and in some sense in a functorial way. So for n equals 4, we just have to add for our compactification finitely many points. For n equals 4, add finitely many. Let me call them limits. Now let's take n equals 5. That's already a little bit more delicate. So we have x equals, now I write it again, 0, 1, infinity, and now 2 parameters s and t. Again, different from 0, 1, and infinity. And if I reorder these special values, I want to have them here, then 1, 1 minus s, 1, infinity, and t minus s. These are again equivalent, as you easily verify. But now you have this kind of fractions here, and you can take s and t going to infinity, but you may want to distinguish how fast they go to infinity. It could be that s goes like t squared or a multiple of t. And that's, you have to decide what limits do you distinguish and which one do you identify. Okay. So for instance, if you take t equals c times s, c dot equal to 1, just a constant multiple, and you take both going to infinity, then x will go to 0, 1, infinity, 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 and y will go to 0, 0, 1, infinity, c, c minus 1. Now you see, here you just get 1 point, but here you get the whole family depending on c, which means that you now have to add curves to get your compactification. Curve in boundary. All this will enter quickly. So now I will define the compactification in one stroke. Compactification via symmetrization. And this goes as follows. I take again d equals 1. If I have time, I'll do it also for d equals 2 and d equals 3. So we have un, let me repeat, this was p1n minus delta n bjs2. And we embed this as follows. So these are now orbits up to pgl2 of pairwise distinct entries of n-gons. And we know that we can choose a representative which has at prescribed places 0, 1, and infinity. So let me take t. This has nothing to do with the t over there. This is for a triple ijk. And this is what? This is the 3-element subset of n over 3. N is just a set 1 of n of labels. And whenever I prescribe such a triple, I can send x to an element where precisely at ijk I have 0, 1, and infinity. And the trick now is I do it for all triples. That's why we call it symmetrization. So we go to p1, n2, 3. Yes. So here I denote the orbit of an n-gon by brackets. And we send it to something which I denote by boldface x. This will be called the string of n-gons. And it consists of a very long string of n-gons, xt, t in n plus 3. Where t is x1t and t. And that positions I, j, and k. If t is I, j, k, I prescribe 0, 1, and infinity. Is this clear? I repeat. You take all possible representatives, all distinguished representatives of your n-gon, distinguished in the sense of having 0, 1, infinity at prescribed places, but we do it for all triples to keep symmetry. So that's a very natural process, and it's easy to see that this is injective.
Why is it in P1 to the n choose 3, not like P1 to the n choose 3? P1 to the n minus 3.
That's right.
P1 to the n, yeah, of course. Thank you.
IJK is a 3-element subset or a ordered?
Subset.
So,
Yeah. We will have quadruples later on which are ordered, but the 3-element subsets.
no, but his concern is that how do you know which one is 0, which one is 1, and which one is infinity if you don't order them?
Yeah, but once you take them as a subset, you order them by increasing.
Oh,
Yeah.
so you want 0 to come first, then 1. Okay.
Yeah, or in any, you can choose.
Okay.
Yeah. Now, inside this here, we have something which I call Zn, and this is a subset of strings which just have the condition that at, again, a vector of n-gons, T, these are all strings of n-gons which have at prescribed entries 0, 1, and infinity. But they don't have to come from a single n-gon. So obviously we end up inside here, but there's an extra condition that when we come from an n-gon, from an orbit, all these xt will be PGL2 equivalent. And in Zn you just have arbitrary vectors of n-gons, okay? So this gives us an embedding, and we define Xn. Let me call this map sigma for symmetrization. We take the image of UN inside Zn, and we take the Zariski-closure, and we're done. That's the compactification. By Zariski-closure.
And how does that compare to Deligne-Mumford, for example? Do you know?
If you just take one triple, yeah, then you lose your symmetry argument, and you prefer, as you have seen above, you prefer one of the limits, not all. You want to keep both. Okay.
It's a different compactification.
Yeah, I mean, then you could just go to Pn n minus 3. Yeah. That's what you don't want. Okay. So a small remark here is that whenever you take a quadruple, if Q now IJ KL is quadruple in N, so this is now an ordered, but not increasingly ordered quadruple of numbers, then we can define the cross ratio with respect to Q of an n-gon by taking just xi, xj, xk, xl, and defining this as xi minus xk, xj minus xl divided by xi minus xl as usual, xj minus the cross ratio. And the cross ratio is an invariant under the action of PGL2. So it is clear that all elements in UN, all these strings here, these will have the same cross ratios. And as the cross ratio is continuous, also the elements in the Zariski-closure will be strings having n-gons with the same cross ratios. Okay, let's write this down.
More information. Cross ratios in the image.
Excuse me?
Is the image determined by those cross ratios?
I'm coming to this. If you give me 1 minute to leave the blackboard. And define Yn inside Zn. So these elements here are again strings E, E in N through 3. And we require that the cross ratio of XP with respect to any quadruplet Q is the same as the cross ratio for all T S in N through 3 and for all Q in N to the 4.
Sorry, but are cross ratios well defined on Zn?
These are not always well defined because they are ratios. That's what I'm also going to tell you. But either you clear denominators, then you may have 0 equals 0, or you just omit those where it is not defined. Yeah.
What was the n again? Is it up there?
These are the strings of n-gons,
Okay.
which have at prescribed places ijk, 0, 1, and infinity. Okay.
Yeah.
I don't want to write it down because it's a very long vector. Yeah. So it would start with the first one would be 0, 1, infinity, something, and 0, something, 1, infinity, something. And it's a long list, but you don't care as long as it is very symmetric, yeah, and systematic. So then it is clear, as we just said, Xn Yn. So this here is a Zariski-closure, so it is connected. This one is given by equations. So this is a algebraic subscheme of Zn. Here we have it. And here we have limits. And we have obviously this inclusion.
So sorry, so Yn is the Zariski closure of the locus where cross ratios are well defined and equal?
You take these here as quality of two quotients.
Yes.
You multiply the denominators, you get a system of equations, many of them 0 equals 0, and the other one will cut out a subvariety here, and this is Yn.
Okay, thank you.
More questions?
Can I?
Yes, please.
Can you explain the map from the Z and to the product of G1s?
This map
Yeah, what is,
is just the inclusion.
how is the n defined again?
Here you have any strings of n-gons, and here you have those with prescribed entries.
I see.
It's only organizational matter. There's no mathematical substance to it. Yeah.
But if you have T just like a tuple, what does it mean to raise each coordinate to T?
I don't raise it to the power T, it's an index.
Oh.
I have to write it upstairs because I need ijk below. Yeah, thank you for asking. Yeah. So this is it. So it is x1 to 1 through 3, x1 through 4, x1 3 4, x2 3 4. Did I miss one? Something like this. Okay, and all these are n-gods.
And you said something about when you're in the case of B equals to 1, you are preferring, you choose just one T and then that's
No, T,
making you preferring one.
T is a triple.
Okay.
T is a triple indexing my n-gods. And I always take entries in P1 for the moment, because it's otherwise notation becomes even more complicated.
So how many limit point are you adding?
Oh, that's a good question. Yeah. I did it in two examples, but in general, you will see how much you add. Yeah, this will come a little bit later.
What about just n equals 4?
N equals 4, you just add, I think 4 points, something like this.
So
I will give you the stratification and the boundary divisor in a moment. Okay, if you have a little bit of patience. Yeah, I cannot do everything at the same time. So, theorem. This was suggested by Joseph Schicho and his student E. And then I was allowed to participate and formulate it a little bit differently. So these two are equal. Then equals Yn. Yes. Smooth, reducible. So you have all the properties you have for M0 n bar. Okay. Smooth, projective. So you have either you have a description as a Zariski-closure and also by equations. Okay. And for free, we get a forgetful map. If we take n plus 1 gone, we can forget about one entry in our n plus 1 gons and go down to Xn. And this is a flat morphism. And it has additional properties I will mention at the end.
What is the dimension?
The dimension is n minus 3. Because it's just a closure of something which is n minus 3 dimensional. So let me briefly mention here case D equals 2 to show you that the same type of constructions works as well.
So sorry, do you know the smallest n where you get something different from the M0 n bar, the usual one?
No, it is the same.
Oh, it is the same.
Yeah.
Oh, okay. I'm not confused.
Yeah,
Thanks.
but to prove that it is the same, you have to use all the machinery Deligne-Mumford-Knudsen are using because their description of M0 n bar. Yeah.
I think there's a construction of M0 n bar where you just take the set of all cross ratios in a big product of P1, which is the closure.
Right. This is by Gerritsen and Herrlich and van der Put. But if you just take the cross ratios, which are of course here behind, then you're not as systematic as with this symmetrization. They run into problems to distinguish where they are. And like this, the proofs go kind of automatic. And moreover, they allow us to use phylogenetic trees. And in the cross ratios, you don't see that. I will come to this again.
So this construction, sorry for keep interrupting.
Yeah.
Would that give a way to get explicit equations for the M0 n bar then?
Yes.
Yeah, it's nice.
I mean, many equations, but.
Yeah, but very explicit.
Okay, to briefly higher dimension. That's often called configuration spaces. In the sense of Fulton-McPherson. So for instance, if D equals 2, we would have again UN P to N minus the special ones, which I call S again, EGN3. But now a new phenomenon appears because in P2, we don't only have to control coalescing of 2 points, they come together, but it could also happen that you have 3 generic points which come together on a line, like in your talk yesterday. So we have to distinguish between incidence and collinearity. And the action of PGL3 is, again, transitive on generic n-gons, on generic orgons, but it preserves collinearity, okay? Action. So, and this makes things a little bit more complicated, but you do the same thing as before. Now you index your strings by quadruples. So now you take Q equals IJ KL. This is not the same Q as for the cross ratio. In N choose 4 element subset. And then you have an orbit. You send it now to XQ, where Q varies here, a string of n-gons, and now you prescribe 4 entries XQ. So XQi will be 1, 0, 0. XQj will be 0, 1, 0. XQk will be 0, 0, 1. And XLQ will be 1, 0, 1. That's your distinguished quadrilateral. You can always arrange, given an orbit that at places IJKL, you're precisely here. And the remaining entries, as you just mentioned, once you fix these here, the other ones of the XQ are given by cross ratios. But now the cross ratios will involve 5 entries, not 4 entries. So you also need higher dimensional cross ratios. For D equals 3, I have to be very brief. New phenomena. Okay. So this genericity which we are using here is due to the fact that we need stability. The stabilizers of the elements of the n-gons have to be trivial. That's the whole business of Deligne-Mumford-Knudsen. And in n equals 3, you have, aside from the generic n-gons, you also have the octahedron, which is stable. So here something new happens. That's why I'm not going to enter too much in details. Okay. Yes.
Do you know how this compactification compares to the chow quotient of the Grassmannian?
Yeah. Yeah. There are many identifications, but I didn't want to talk about chow quotients today. Yes.
Okay. All right. I can ask you.
For D equals 2, what about you have like 6 points of ionic conic? Then, I mean, don't they have different orbits?
Can we do this in private communication? Because I am running a little, I want to talk a little bit about phylogenetic trees as well. Okay. So, second part. Phylogenetic trees. Now, there's one approach to these moduli spaces using topicalizations, and they are metric phylogenetic trees appear. Here they will appear in a different setting, which I want to explain now. And I do again D equals 1. And we do the following. We take X equals T entrance 3, Yn. So this is now a string with n-gons with equal cross ratios whenever they are defined. And in order to prove this theorem, we will use the construction of a graph associated with such a string, which will be a phylogenetic tree. And we will use the combinatorics of phylogenetic trees to prove the theorem. Okay, so it will be completely elementary. So let me recall xt will be, yes, that's fine. Associate to X the following graph. I call it gamma X. And I guess I do it over there. X, E, 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 E1, and E. Please don't care about these huge numbers which appear here. We just treat them as black boxes. So the vertices of the graph will be not the n-gons which appear here. Some of the n-gons of such a string may be equivalent to each other, others may not be. But as we have finitely many, we will get finitely many orbits. So we can associate to X the set of orbits T, 3. Oops. And as you have seen in my limit construction, actually we will have different orbits in one string. So the vertices are just the orbits. And the edges, so when do we connect two orbits an edge? If and only if xt and xs, I write it down and then I will explain, have complementary incidence sets.
So could you clarify this X is taken from where? From the target set, from the Zariski-closure, from the image, where?
Equal cross ratios.
Equal cross ratio.
Yeah.
Okay.
And a posteriori, we know that this is the closure.
Right,
I
right.
use only the equations of the cross ratios and not the Zariski-closure is kind of intransparent. But the equations with the cross ratios I can easily work with. Okay.
So on the point of the image, do I just get one vertex? Are all of those equivalent?
No, yeah, on the open then set, you just get one vertex, yeah.
Right.
Of course, for the generic X, you will get one orbit and no edge. Okay. So what are the incidence sets? I guess I do it by example. Let us take n equals 5. So we get 3 orbits. That's one example. X. Now I just write X and I don't write the triple above. You 0, 1, infinity, infinity, infinity. Y equals 0, 0, 1, infinity, infinity. On Z equals 0, 0, 0, 1, infinity. So this here would be t equals 1, 2, 3. Of course, t is not unique. Here we would have 1, 3, 4, And here we would have E equals 1 or 4, 5, for instance. Okay. These are the places where I have prescribed my entries. Okay.
When you say complementary, do you mean disjoint?
I'm just explaining it.
Oh,
I'm explaining it in this example. So what is an incidence set? These are indices or labels where the entries are equal. So we have color. In this one, we have this incidence set. These three are equal. Here we have two incidence sets. Here we have this one. Okay. Now, as you see, this guy has a complementary incidence set to this one, because here we have 1, 2, 3, and here we have 4, 5. And the same happens here. This one is complementary to this one. So complementary partition of our set capital N. Okay.
So those incidence sets, they can appear not only on 0, 1, infinity, it could be also some other number.
Right. Yeah. So in this example, you see this one is kind of special. These two are symmetric to each other. So we get 3 orbits, and we have X, Y, and Z.
Sorry, what group is the orbits of what group is this? Is because I mean I don't quite because this is a big dimensional variety and PGL2 just is a small. I'm not quite sure why we get finitely many orbits when there's n equals 5. It's a big dimension.
Well, of course, you could have families here, but I'm just exhibiting one type of string where you have these entries. Yeah, I cannot do it all at the same time. Yeah, I will show you more elements later on. Okay. I want to explain this definition here. Okay. To complement, you choose in your n-gons sets where the indices, where the entries are equal, and then you draw this graph. Okay. The next step is to look.
Is like just full capital X includes X, Y, and Z in the string? Is that?
Yeah, here we have a string which has, we suppose that it is a string with 3 orbits.
Okay.
Yeah. I will draw you all the graphs of all strings for n equals 5. Okay. I just want to first define the construction. Moreover, you see that you have entries which are different from all other entries. Here, 0 and 1 are distinct to all others. Here it is just 1. And here we have these 2. You agree? These are called singletons. Yes. And now you observe that here you have it first place, second place, third place, fourth place, fifth place. All places occur as singletons, which is not a coincidence. It is true always. Okay. So now we attach to these 3 orbits leaves by attaching their singletons. So X has 2 singletons, which will now be labeled. They are 1 and 2. That is symmetric. And we get 4 and 5. And Y has just 1 singleton, which is 3. Okay. So lemma or theorem, whatever you want. Whenever you draw this graph, you can attach to the vertices leaves labeled by the numbers 1 up to n. And each label goes to precisely 1 vertex. Okay, so let me write it down. The leaves attached to vertices, singleton labels. The labels are the indices of my entries.
Why is X and Y connected? What is complementary?
Yes, I mean, here you have 4, 5, and 6. This is one incident set. Because infinity is equal to infinity equal to infinity.
Me 3, 4, 5.
What did I say? Yeah, 3, 4, 5, and here you have 1 and 2.
You don't care about the 4, 5.
No, this one goes with this one. Yeah. So complementary means they have 2 incident sets which are complementary, give a partition of the flat capital N.
I so you can choose parts of and then.
Yeah, as I did.
Ah.
You're confused? A little bit.
I'm a bit less confused now about how to explain.
Yeah. So this is a phylogenetic tree, a labeled phylogenetic tree. Theorem is gamma x, well, we have it, this is for d equals 1, gamma x is always n labeled phylogenetic tree. And you get all phylogenetic trees. And all, okay, this is 3. So I have a little bit of spare space here. For n equals 5, we can get 3 types of phylogenetic trees. This one, now let's do the exercise together. This tree corresponds to which string? We have one orbit and all entries.
General.
This is a generic one.
But sorry, so I have a question. So by phylogenetic trees, you mean just trees?
Yeah, but no vertices of degree 2.
Okay.
No vertices of degree 2. The leaves are the vertices of degree 1, and the other ones have at least 3. And this 3 is the same as which appears everywhere in this business. Okay.
Is this the dual graph to the stable curve?
Yes, of course.
Okay.
Yes. Yeah. But I have to finish soon, so I cannot do what I wanted, but never mind. Let's do the next example here. We could have 2 orbits. And now you have to distribute your leaves. And this is, somebody asked, what about the one-dimensional strata? This is the whole family. A one-dimensional family of strings having this phylogenetic tree. And the last one is the one I just gave you is 3. So you see, it's kind of fun to draw these trees. If a nice one for n equals 6, I want to give you another one. It was nice. We call it Riebistel. I don't explain why we call it Riebistel, but you can look up in the Google Translator what it means. Okay. So here you have 1, 2, 3, 4, 5, 6. So you have one vertex, so one orbit, which has no singleton at all, but it has 3 ramifications, so the condition for the phylogenetic tree is fulfilled. Okay. So this gives you automatically a stratification of X and Y. This gives stratification.
Sure.
Yn by the constancy of these phylogenetic trees. So whenever you take all strings which have the same phylogenetic tree, then you get a stratum inside your variety. It's a natural stratification, and the adjacency of strata is very easy to be seen. So this one is the n-3 dimensional open stratum. This one is in the boundary, yeah, and you get it. You go from here to here by just contracting this edge here, and here you contract this one to get here. So you see the adjacency in the trees. Okay. Now I have 2 minutes left, which is fantastic, but I will give you just one hint how you prove the smoothness. Of X and Y. So assume you have this kind of tree. That's not good. I have to omit this one here. Okay. So proving smoothness means you have to construct charts where you rectify your variety on an open neighborhood. So what you do is the following. The charts are parametrized. So then you have your huge space Yn. You choose certain strings X in Yn and open neighborhoods, which I call Ux in a special way. I cannot explain it now. So you get a covering of Yn, and you prove that these open sets are isomorphic to an open set of Pn-3. Okay? And how do you do it? These selected strings and neighborhoods correspond to what we call extremal graphs, and you delete one edge. In the extremal graphs, you have precisely n-3 edges, and you delete also the endpoints of this edge. So you get n-3 ways to delete an edge and its endpoints. So this gives you 4 components, 4 connected components in your graph. In each component, you can choose, that's now by choice, the minimal label. One here, one here, one here, and let's say one here. So you get 4 labels. It's not unique, this choice, but you just do minimality to simplify your life. So you have 4 labels. So you can define a cross ratio with 4 labels. 4 labels Ij, L, and J, L, and they will give you the cross ratio Ij, L of X. All the cross ratios are the same if they are defined, so we can write it cross ratio of the string, and this gives you an element in P1. Like this, you get n-3 elements in P1, the cross ratios, and you prove that all other cross ratios can be constructed from these selected ones. And so you have an inverse map, and you are done. So this was an idea of Joseph. I don't know how he came up with this idea to just delete one edge, but it works. And all the other proofs go in a similar method. For instance, you have the concept of meeting point. If you, now I draw this again. If you choose this label, and this one, you have a unique meeting point, which is this vertex where the paths meet for the first time. And so you have a whole business of manipulating with your phylogenetic trees. Okay. Can I do one more minute? What is the graph for two-dimensional strings in P2? So now we have again a string now x q in n over 4 with equal cross ratios. And the vertices are again the orbits. But the edges are now defined differently. The edges are not defined by complementary incidence sets, but by complementary incidence set with a collinearity set. So incidence xt, this point union collinearity xs. Oh, sorry, that's not t, that's q and r whole n. Is it clear what I mean? So I give you the example. Now this is what we call type 14. We have 6 orbits, and I just give you the incidence sets. The first orbit has 1 equals 2 equals 3. I hope the meaning is clear. You have this is for n equals 6. So this is an orbit where the first entries of our 6 gon are equal, and the other ones are generic. B is 4 equals 5 equals 6. C, 1 equals 2 and 4 equals 5. D, oh, you cannot read. Let me continue here. Sorry for the mess. D is 1, 2, 3 equals 6. Now, collinearity is expressed like this. We just write it in brackets. So this means 1, 2, 3 are on the line, and 3 is equal to 6, so also 1, 2, 6 are on the right line. Okay. And 4, 5, 3 equals 6. E, 1 equals 2, 3, 6. 4, 5, 6. This is a line again. The last one is 4 equals 5. 3, 6. 1, 2, 3. So I repeat, this just indicates in this orbit the first 3 are equal, and then here it means that 4 and 5 entries are equal. These are aligned, and also these are aligned. And now I connect. How do we connect? So for instance, these two have this incidence at 1, 2, 3. So we look for an alignment set 4, 5, 6. That's easy. It is here. So we connect E and A.
Also D has 4, 5, 6.
D is not okay because it has a 3 involved.
Still 4, 5, 6 are on the line.
Yeah, but I have to count all. I have to take a maximal set of this.
Okay.
But otherwise it doesn't work. I mean, okay?
Okay.
So let us draw the graph together. So what would you connect? A goes to, as we already said, goes to F. E. To E, yes. Sorry. And then E is connected to, I have it here, so I don't have to. E is connected to D. Because 4 equals 5, and here we have the complementary set aligned. This is alignment, parentheses are alignment. So C and D are connected, you agree? And also D. Okay. So we get D. And now by symmetry, you go to F and then you go to B. Okay. This is a graph, which is not a phylogenetic tree. And it has no leaves. So where are the leaves? So the singletons don't work. But now we can take singleton lines. Single lines. So repeat, these are sixgons. Sixgons define lines. And we can look in each sixgon whether this line is unique. So it does not coincide with another line. That's what I call singleton lines. And they are indexed by pairs of labels. Pairs of labels. And then you just look for A. What are the lines which are alone? Here. So the line 4, 5 is certain, because 4, 5, 6 are generic. So 4, 5 will not coincide with any other one. 4, 6 and 5, 6. So we get 3 lines here. 4, 5, 4, 6, 5, 6. And I continue. Here we get 3, 4. Here we get 3, 5. In C, we get 3, 6. In D, we get 1, 4, the line 1, 4, the line 1, 5, the line 2, 4, the line 2, 5. In F, we get 1, 6, and 2, 6. And in B, we get 3, 1, 2, 1, 3, and 3. And now you get a kind of strange graph. We call it kite graph. You know now why we call it kite graph. Because it looks a little bit like a kite. And you observe that the singleton lines, each is attached to a unique vertex. You have all pairs of labels, and each is attached to a precisely one vertex. And that is 0. Thank you very much.
Questions?
Does smoothness fail for D equal 2, or is it true?
We don't know.
How about the relation to the chalk quotient of corresponding D,
Yeah. I expected this question, but you can use gain duality and embed it in the chalk quotient and relate it to it, but we didn't work it out in detail yet. Yeah. But of course, there is a very strong relation to chalk quotient.
We don't know whether it's the same or not the same.
No, because in first instance, we don't know how to characterize these graphs. They will stratify again. They exist for D equals 2. They always exist. They always have this shape. Yeah, but we have no combinatorial description what kind of graph this is.
But the chalk quotient of corresponding 3, n has a combinatorial description of the strata. So if you can find the sort of match.
Yeah. Okay. Sure. Yeah.
You mentioned the Fulton-McPherson
Yes.
space for P2.
Yes, the configuration space. That's so. So for D equals 1, we have the complete theory. For D equals 2, we are still trying to understand what's going on here. Yeah, because there are all the different labelings one can choose. Yeah, and only to prove that this really exists is tough. Yeah, because it's not a deep result, but it's tricky. It's tricky to see. Of course, the goal would be to do all dimensions in a systematic way, but already the d equals 1 case is 60 pages. So. But maybe I should emphasize, you know what, in this business, you know what you should expect because you already have the complete theory at Deligne-Mumford, but you want to find proofs in terms of this. And the funny thing which happened over and over again, you look at the phylogenetic tree and it gives you for free a strategy of proof. And that's very nice because then you just work out the details and you're done. I never had this experience that you have kind of a teacher aside who tells you do this, this, and this. For instance, if you delete these, one thing I should say, I mentioned it's no longer here. We have this map from Xn plus 1 to Xn. So we prove that the fibers of this map, so Xn, maybe I write this down. We have Xn plus 1 to Xn, natural forgetful map, forgetting an n plus n one entry, and we get for free n sections, n plus 1 sections, sorry, here. And we prove, again, using the phylogenetic tree, that the fibers are n-pointed stable curves. So they appear for free in this business. So it's, in some sense, the circle closes as you, how did you call it, Schließungssätze? This is maybe the hardest part to prove that it gives n-pointed stable curves, and you can also see that you get the stratification, you get the boundary divisor as normal crossings, you get everything.
Okay, let's save more questions for lunchtime.